So today we will be discussing the aircraft refrigeration system, which is a part of refrigeration and air conditioning subject, and it is divided into two categories. First is the theory part, which we are covering presently. This presentation is divided into four different parts. First is the why necessity of cooling an aeroplane, its basic cycles, reverse Carnot, reverse Brayton, Bell column, the fundamental cycle behind this air refrigeration system. Then different type of aircraft refrigeration, its working, and TS diagram basically. These are four basic systems for aircraft refrigeration. One is a simple bootstrap, reduced ambient, and regenerative air refrigeration system. So that part we will be discussing in this. The necessity of the cooling an aeroplane. So why it is required to cool the aeroplane? Like at very higher level the temperature is very low, so why it is required to cool the aeroplane? So as we have discussed previously, that the cooling or air conditioning is not the lowering the temperature. It is four different parts. Apart from lowering the temperature or conditioning the temperature, we need to fix the airflow rate or air velocity and concentration of contaminants, as well as the temperature and overall temperature of the aircraft. So aircraft refrigeration system are required other than the generation of heat from the human, like solar radiation, avionics, means different aircraft parts which may contribute the rate of increase of heat, ultimately the increasing the cabin air temperature. So with the technological development of high speed passenger and jet aircraft, like now it is more than 400 passenger carrying aircraft, so what you are going to do, you need to control all the circulated air throughout the airplane. In fact, some of the aircraft which is having larger goods compartment also needs to be air controlled. Next is the air is cheap, it is safe, non-toxic, non-inflammable, and also if air is going to leak from some of the part, it's not a problem unless the leak can be minimized within the specific time. Cooled air can directly be used for cooling because at certain height from the ground level the air is available in the cool condition. So low temperature, low weight heat exchangers can be used, ultimately contributing towards the overall weight of the aircraft. And the compressor, separate compressor is not required, because the compressor which is used in the aircraft can also be spared, and design and maintenance are the simpler. So these are the few of the necessities required. Before we start for the fundamental cycles, it is important to understand the assumptions. First is the working fluid is a fixed mass of air, because air behaves as an ideal gas. Second, the cycle is assumed to be a closed loop cycle. All the processes within the cycle are reversible, and the specific heat of air remains constant throughout the cycle. First, we start with the reverse Carnot cycle. So reverse Carnot cycle is the ideal cycle, and it is the reverse of standard Carnot cycle. It consists of four processes, two isothermal and two isentropic process, which is visible in the pressure, volume, and temperature entropy diagram. So in the pressure volume diagram, it starts from point 1 compressor, 1 to 2, 3 to 2 to 3 is condensation, 3 to 4 expansion, and 4 to 1 is the evaporation. So entropy is constant, so 1 to 2 and 3 to 4 isentropic process, and 2 to 3 and 4 to 1 are the isothermal process. Simple reversed Carnot cycle. So the limitation of reverse Carnot cycle is why why cannot apply the fundamental or reverse Carnot cycle in aircraft refrigeration, because it is very slow, and isentropic process it is supposed to be very fast. So the combination of isothermal and isentropic process may not be possible and may not be achieved directly, so ultimately leads to the limitation. After reverse Carnot cycle, reverse Brayton, or you can say Bell-Coleman cycle. So there are different diagrams in this slide. First we start in the extreme right corner. This is the TS diagram of reverse Brayton cycle. So 1, 2, 3, 4. So it's two constant pressure cycles basically. Lower pressure, higher pressure cycle. So two isentropic process, and it's not isentropic process, it's a adiabatic process. Similarly, the Bell-Coleman cycle also consists of process which is having slightly lower pressure zone, lower and higher pressure. Otherwise, the nature of the cycle are same. And this is the PV diagram of the cycle. So these are the two TS diagram, and the other is the PV diagram, which is giving the isentropic expansion and compression during this refrigeration cycle. In reverse Carnot reverse Brayton cycle process, different process like irreversible process, all adiabatic and isentropic processes are happened inside all the standard refrigeration cycle parts like compressor, heat exchanger, turbine and heat exchanger. We can also calculate the actual reverse Brayton cycle and Bell-Coleman cycle. And what is the difference? Difference is the 1 to 2 and 3 to 4. So if you go to the standard cycles, you will find that the 2 is slightly beyond the standard 2 point. Similarly, the point 4 is slightly inside the point 4 due to the different heating, reheating and cooling process. So ultimately, all these cycles, if you compare here in the fourth picture, where reverse Brayton and reverse Carnot cycle are compared. So 1, 2 prime, 3, 4 prime is the Carnot cycle, 1, 2, 3, 4 is the reverse Brayton cycle. So you can directly say this lesser area with lesser range of temperature is covered. However, the lower temperature is achieved in the reverse Brayton cycle. Now we will start with the simple air cooling system, or you can say it's the simple aircraft cooling system. So what are the cooling conditions? 1, large internal heat generation due to occupants, equipment, etc. Second, heat generation due to skin friction caused by the fast moving aircraft, RAM effect and solar radiation. So these are the requirement of the aircraft. Air cycle refrigeration is preferred in the aircraft generally because it is cheap, safe and so many conditions. And also this is the system which is used during the movement of aircraft on ground running condition. This is the only part. So in this aircraft simple air cooling system, this is the cabin, or extreme right up to the first figure. This is the cabin, point 6, where the cold air is to be circulated. Before cabin, it is attached to the cooling turbine, where shaft of the turbine is used to drive the fan as well. So this fan and the turbine is connected through a heat exchanger. In heat exchanger, the RAM air is supplied through the compressor, and it is also supplied through the main combustion chamber. So this is called bleed air basically, which is to be supplied. So one point is RAM. This is the aircraft engine. So air is circulated from here and supplied to the heat exchanger, then cooling turbine and cabin. So point 1 outside air, 2, 3, 4, 5 and 6. 6 is the point where is finally separated. So 1 to 2 process is basically isentropic ramming of air, 1 to 2. Then 2 to 3, this is vertical. But actual process, actual compression of main compressor, 2 to 3. Then 3 to 4 is the constant pressure heat rejection and heat exchanger. Similarly 4 to 5 is the actual expansion in cooling turbine, and 5 to 6 is the constant pressure heat addition in cabin. So from here to here the air is supplied inside the cabin. So in overall, in this simple air cooling cycle, ambient air gets rammed before the main compressor, or we can say low outside pressure and low temperature air is compressed due to the ram effect. Then cold air at state 5 is supplied to the cabin, which picks up heat and it flows throughout the cabin and ultimately providing the cooling effect. And the power output of the turbine is low because it is also used to drive the fan. So due to irreversibility, the actual pressure at the end of the ram will be less due to the pressure resulting from the isentropic compression. The simple system or simple air cooling system is good for ground cooling, or specifically when aircraft is not moving, as fan can continue to maintain airflow over the air cooling system. After basic aircraft cooling system cycle, the next is bootstrap air refrigeration system. So from this schematic diagram of bootstrap system, it can be shown that there are more turbines and more heat exchangers are used into this system, bootstrap system. So what is going on? The system consists of two heat exchanger, before and after, air cooler, after cooler. It also incorporates a secondary compressor which is driven by the turbine at the cooling system. This system is suitable for high-speed aircraft, where the velocity of the aircraft provides the necessary airflow for the heat exchangers. A separate fan is not required because it is not suitable for the ground running condition. So in that aircraft cycle, because this is the ambient air, it is rammed in the compressor through the turbine combustion chamber. It flows to the heat exchangers, two heat exchangers and compressor, and from there here it is going to supply to the cabin. Now this is the first point, ambient air. It is from 1 to 2, the isentropic ramming of the surrounding air, ultimately reducing the pressure. Then from point 2 to 3 prime, so 2 to 3 prime means up to here, the actual compression of air as a result of inward due to the irreversibility. Inward means inward of the aircraft engine. Then from 3 to 4, so 3 to 4 is the cooling of air in the primary heat exchanger, so pressure drop is neglected. Then 4 to 5, isentropic compression of cooled air from the main heat exchanger. 4 to 5 actual compression. 4 to 5 is actual compression, and this is isentropic, and this is actual compression. And 5 prime to 6, cooling of ram air in the second heat exchanger. So drop of pressure, because it is slightly lower than the before compressor process, so it can be neglected. 6 to 7, then isentropic expansion of cooled air in the cooling turbine. 6 to 7 actual expansion of the cooled air, and 7 to 8 is the heating of the air in the compartment temperature or cooling temperature, 7 to 8. So this is the part where air is going to supply. Next is reduced ambient air refrigeration system. In that system also there are two turbines, and the same shaft is used to drive the fan. So earlier fan was not there, now fan is introduced here. Apart from the reduction in heat exchanger, also there is one heat exchanger. Now two turbine, one heat exchanger. So reduction here it is used with the cooling fan. So slightly it is to be used very high speed aircraft application. Very high speed where heavy temperature is too high to work as a good coolant. Expands to the first cooling turbine before it is in the heat exchanger as a coolant. Temperature is less than the initial temperature to ram air. So in that temperature 5 is the point where it is to be supplied in the cabin. 1 is the outside air temperature. So this is outside air, ram air, compressor. This compressed air go to the heat exchanger. From heat exchanger it is supplied to the fan and to the exit. Then from this fan it is supplied to the cooling turbine and to the cabin. In regenerative air refrigeration system, on the right side there are two figures. So this shading figure, basically this is the combustion chamber, ram air compressor, again two heat exchanger, one turbine, and this system is going to be used by the air temperature. So 1, 2, 3, although the actual it is 1 to 2 prime. If you go to the left side of the page, this 1 to 2 prime represent the actual ramming of the air. Now here the friction and other losses are considered in regenerative air refrigeration system, so that whatever losses different part in the system can be used to produce the cooling effect or to increase the efficiency of the cycle. So 1 to 2, 2 to 3 to 5, 6, 7. So 1 is point where outside air is introduced, and point 7 where it is supplied to the cabin. Otherwise all the processes are almost same, although this is regenerative cooling, so automatically from 3 to 5 the reduction in temperature is much more in comparison with the other air refrigeration system. So these are some of the informative discussion for different type of air refrigeration system. There is some because all the refrigeration system are quite old. Some small developments were there, but there is no significant development for air cycle refrigeration. So I have tried to summarize few air cycle refrigeration system which can be used, although there are a lot, but few of them are very much popular and may give the significant future in case of air cycle refrigeration. First is acoustic refrigeration. So basically acoustic means the use of sound waves. Sound waves can be used in the refrigeration system because it can also the carrier of the heat. So there are still some work research work is going on. Air cycle refrigeration means instead of using the ram air, we can use some air pockets in different zones so that it can be used to reduce the temperature. Air pocket cycle type air cycle refrigeration. Then electrocaloric means the use of electricity because electricity is also the carrier of heat. Then hydraulic refrigeration, different type of hydraulic systems can be used. Nuclear refrigeration also popular in the food industry, where the perishable food life can be shelf life can be increased. Magnetic refrigeration, although it has very high potential, but till now we haven't have any significant research in that field, but surely it's a promising research area. Optical cooling is related with the light energy. It can be used to, because light can also the carrier of heat, so in the opposite we can obtain the heat cooling effect. So Peltier effect, Stirling cycle, thermoelectric refrigeration, and these are the other type of refrigeration system. Also it is available in the different part of the world, so that at specific application it is being used. The aircraft refrigeration basic fundamentals are over, and numerical part is also released very soon. After this covering of these parts, the psychometric and air conditioning process will be discussed.